Hello all, we're going to go through the rest of Chapter 2A topics. So this topic here is using the periodic table to identify similar elements. We've talked a bit about elements now, and now we're going to look at the elements' placement on the periodic table. Notice the different colors here. So in green, these are all metals. In a sort of light blue, these are all non-metals here. Then these elements here that can't really be classified as metals or non-metals, they're found in this sort of staircase pattern here. One element that is a little bit out of place, but it's important to know, is that hydrogen up here is definitely non-metal. It's not a metal. So there's a few different things to think about here. So metals are more similar to each other than they are to non-metals. Similarly, non-metals are more similar to each other than they are to metals. So from these first two bullet points, we could say that metals are more similar to one another, as well as non-metals are more similar to one another than they are to metals. This third bullet point, though, is also extremely important. Elements in the same group, remember how we distinguish group and what that means? The different groups are the vertical columns in the periodic table. Okay, so importantly, we call the groups these columns, whereas the rows, for some terminology to also be aware of, these are called periods. Okay, so we have groups and we have periods. This point is really important because elements within the same group, meaning the same column, are most similar to each other. Some anomalies to watch out for, though, is that hydrogen is still a non-metal, so it's more similar to these other non-metals than it is to the other elements that are in group 1. So watch out for hydrogen, as it's a little bit unique in that way. And so if elements in the same group or the vertical columns are similar to one another, then for example, we could say that oxygen has some similar properties to sulfur. Similarly, we could say that magnesium has some similar properties to calcium. Here's more of what we just went over. So most elements are metals, and you can tell the metals were in green here in the periodic table, whereas these non-metals are over here. And what elements can't be classified as either metals or non-metals are these metalloids. And so again, those are in this sort of stair-step pattern here. And now here's this terminology that we just learned. So groups are these vertical columns, whereas periods are these horizontal rows. We're going to go through each of these categories now and talk a little bit more about these different groups. Here's a little bit bigger of an image so you can see where the alkali metals fall, the alkaline earth metals fall, the halogens, and the noble gases. It's important to start to get really familiar here with these names. So group 1, the first group, are the alkali metals. They're in group 1. So you might see it represented numerically, also maybe with Roman numerals as well. Then the second group over, or the second column, these are the alkaline earth metals. So we have alkali metals on the left-hand side. Hydrogen, again, is not a metal, and hydrogen is also then not one of the alkali metals. Remember, hydrogen is a non-metal. So hydrogen is one of the exceptions here. It's a non-metal, even though it does appear in group 1. So group 1, we have alkali metals, and then group 2, we have these alkaline earth metals. The next groups to be familiar with their names is going to be the halogens. These will be really important, as well as the noble gases. I should say all the groups are really important, especially these names though. So the alkali metals, alkaline, halogens, and noble gases. One thing I want to point out here is group 17 are the halogens. These can also be referred to as group 7A. So one thing that could get a little bit confusing and something to be aware of when you're looking at the periodic table is this group here, this column here, is group 16, but based on the organization of the periodic table, it's also referred to as group 6A. Similarly, the halogens are in column 17 or group 17, but you will also hear them referred to as being in group 7A. Then can you guess what's here for the noble gases? What's being covered up by this label here? So we have group 18, but also called group 8A. So just for a little bit of a visual here, more on that because it can be a little bit confusing to get used to, is we see group 1, group 1A, group 2, group 2A. Then when we get to electron configurations, this will become more clear, but essentially sometimes we sort of ignore these groups here, these column numbers. So we go from 1, 2, all the way here to 3, 4, 5, 6, 7, 8. So you will hear me say the halogens are in group 7, group 7A, I should be saying. Noble gases are in group 18 or 8A. So that little bit of organization there is definitely something to start getting comfortable with, get familiar with, look at the periodic table, see what's happening there. So as we talked about in group 17 or group 7A, we do have those halogens. To the right of the halogens in group 18, or also we could say in group 8A, we have the noble gases. These four main distinguishments are important to know. So the alkali metals, alkaline earth metals, halogens, and noble gases. And also start getting really comfortable that we are working in groups when we're talking about those columns, and then periods are the rows. Also get comfortable recognizing what is a metal, a metalloid, and a nonmetal. Another piece of organization here as we're talking about just the layout of the periodic table is what the different periods are. So periods are the rows, but to let you know, this is going to be period 1. So period 1 entails hydrogen, and then we draw a line over here, and helium. We go one row down, that's period 2. It has lithium and beryllium, and we go over. These elements are also all in period 2. So we know elements are similar if they're in the same groups. But what about elements that are in the same period? For elements in the same period, they have similar electron configurations. We will get to electron configurations towards the end of the semester, so a little bit later on. One other thing I wanted to point out, because this is the version of the periodic table you can use on your exams, it is available on Canvas. So as I mentioned here, we can have group 13, 14, 15, 16, 17, 18, also group 3A, 4A, 5A, 6A, 7A, and 8A. The only other thing I wanted to point out here is that you can also see them represented as their Roman numerals. So that's 3, 4, 5, 6, 7, 8 in the Roman numerals. So right now we could look at the periodic table and figure out what is a metal and what's a nonmetal. I want you to practice working on distinguishing what is a metal, what is a nonmetal, and what's a metalloid, also on this blank version of the periodic table, because on an exam, you won't have that colored in version to know exactly right away what's a metal, what's a nonmetal. So go ahead and practice recognizing on this blank version, be able to draw out for yourself metals, nonmetals, and metalloids. So when we recognize that two elements are both metals, an example of how they can have similar properties can be seen here. So they both have very high melting points. They're both metals. Similarly, both phosphorus and sulfur are nonmetals. They have lower melting points. Something we're going to talk about later on in chapter 2 is this idea that these metals will form ionic compounds with oxygen. We'll come back to ionic versus molecular compounds. To start to get you familiar with this, a metal with a nonmetal like oxygen will form ionic compounds, whereas two nonmetals will form molecular compounds. This will be really important when we start to do naming of compounds later in chapter 2. Now, something we're going to get to next is this type of ion formed, where metals, you can see they form these cations. Nonmetals will form anions. These are all examples of metals, and they all form cations. So what do we think a cation might be? We're going to cover this a lot more in depth. Cations are positively charged ions. So now we're going to go into counting protons and electrons in atoms and ions. So we'll go a lot more into this topic, this idea of what is an ion, cations and anions. This is a reminder from Chapter 2A, Part 1. So we covered this. Briefly here, we're going to use the atomic number to distinguish the identity of the element, where the atomic number is always the number of protons. It's the identity of the element because, for example, all carbon atoms all have 6 protons. Every isotope, every atom of carbon will always have 6 protons. The atomic number is how we distinguish what the element is, along with its chemical or element symbol. So we know how to find the number of protons using the mass number then, or the atomic mass, atomic weight. We know that's the number of protons plus neutrons. So to find the number of neutrons, we can take the mass number and subtract the number of protons to get the number of neutrons. Okay, so that's stated here. Now, to determine the number of electrons, we're going to get into more today. If the atom is neutral, then the number of protons, so aka the atomic number, will equal the number of electrons. However, this is not always the case because we don't always have neutral atoms. For non-neutral atoms, these are called ions. For ions, the number of protons will not equal the number of electrons. There's 2 different kinds of ions. There's cations and there's anions. One cute way to remember this, cations are positively charged. To take this example here, cations have a positive charge. That means that cations lost 1 or more electrons. I was going to use carbon as an example. Let's use calcium here. When we go to the periodic table, we find calcium. We recognize its atomic number is 20. That means that calcium has 20 protons. So calcium has 20 protons. For neutral calcium, so something that doesn't have this 2+ here, then that calcium atom will also have 20 negatively charged electrons. This net charge here needs to be 0, so 20 positive charge and 20 negative charge for a neutral atom. What about calcium 2+ then? Well, remember it's calcium, so the number of protons will never change for that same element. Calcium has 20 protons when it's neutral. Calcium has 20 protons when it's positively charged. Calcium itself is an element with always 20 protons. That is the identity of calcium. So calcium 2+ has 20 protons, but we see here it has this overall net charge of 2+. For the number of electrons then, how many negatively charged electrons does calcium need to have to make this net charge be 2+? Well, calcium 2+ can only have 18 electrons. So a positive 20 with a negative 18, that net charge is 2+. So neutral calcium, 20 protons, 20 electrons, overall net charge of 0. A cation of calcium, so calcium 2+, for example, that means that calcium's neutral atom lost 1 or more electrons. How many electrons did it lose? Well, it must have lost 2 electrons. How do we figure that out? Calcium went from 20 electrons in its neutral state to only 18 electrons now as a cation. So on the other hand, the other type of ion we can have is an anion. An anion is an ion with a negative charge, meaning that the neutral atom gained 1 or more electrons to now have extra electrons to be overall negatively charged. Let's look at chlorine now. Chlorine has an atomic number of 17. Chlorine's atomic number is 17. That means it has 17 protons. Chlorine is neutral, so we wouldn't see this minus sign here as a superscript. We would just see a Cl atom like this. For the neutral chlorine atom, it must have also 17 electrons for an overall net charge of 0. Let's talk about the anion now of chlorine. The anion of chlorine has an overall net charge of -1. How many electrons must this anion have then to have an overall net charge of -1, given that it has 17 positively charged protons? Well, this means that this anion of chlorine must have an additional electron. So 18 electrons with 17 protons, that net charge is -1. There's one extra electron relative to the neutral atom of chlorine. One thing when we'll get into more naming is we actually call this a chloride anion. That IDE ending is something you'll see a lot more later on in chapter 2. So just another visual here of these cations and anions. A neutral sodium atom will have 11 protons and 11 electrons, whereas a cation of sodium will have still 11 protons, of course, it's sodium, but now it's lost one or more electrons. Here it's lost one electron to be overall positively charged. Here's a visual of chlorine. We went through this example, 17 protons and 17 electrons for the neutral atom of chlorine. For a chloride anion now has this negative charge. That must mean it's an anion where it's gained one or more electrons. That means 17 protons, but now one additional electron, so then 18 electrons here. As one quick reminder from chapter 2a part 1, we talked about isotopes. Just to keep you on track here, isotopes have a different number of neutrons. Remember, so then isotopes, different number of neutrons, ions, different number of electrons. For protons, that number doesn't change, right? Because it's the identifying factor of any given element. Something important we'll get into as well, more with naming, is the difference between a monatomic and polyatomic ion. Mono meaning one, just to keep consistent with the colors. Poly meaning many. So from the name here, a monatomic ion is an ion that just has one atom. Then as you can see here, for a polyatomic ion, that's going to be an ion, meaning it has an overall charge, right? Be it positive or negatively charged. A polyatomic ion has more than one atom. For example, here we have this polyatomic ion, this polyatomic anion specifically, that has both oxygen and hydrogen. So this distinguishment will be really important when we get into naming. So monatomic ions, polyatomic ions. This table can be really handy now to start getting used to which elements form which kinds of ions. As you may start to notice here, the different ions that each element can form are pretty predictable, and it has to do with their electron stability. What does that mean? It means that all of these alkali metals, right, they're in group 1, will be stable as cations with a +1 charge. Similarly, all the alkaline earth metals will be electronically or electron stable when they lose 2 electrons to become +2 cations. Then some more patterns over here that get predictable is that these halogens are stable when they gain 1 electron to become anions. These nonmetals here in group 6A can gain 2 electrons, it looks like, to become -2 anions. The pattern continues here as well for nitrogen, phosphorus, and carbon. Notice -3 and -4. What can we take away from this? Well, it looks like over here, cations form predictably, and then on the right-hand side, anions form predictably. Importantly here, there are some elements that get a little trickier to deal with because some of them will actually form 2 different kinds of ions. For example, iron can be stable for its electron configuration in both a +2 and a +3 cation configuration. Another one here, silver can form +1 cations, So it's important to get comfortable with these different patterns that we can see in the periodic table for what ions form specifically. To show this explicitly here, as we talked about, group 1 alkali metals can form +1 ions. Alkaline earth metals form +2 ions. These are both cations, right? Cations are positively charged. Cations are positively charged. Next here, group 15 or group 5A, we know we can call this as well. These elements up here typically form 3- anions. We go over one group, right, to group 16 or group 6A. These predictably form -2 anions. Another important one here is that the halogens in group 17 or group 7A, they will predictably form -1 anions. Okay, so it will be important that you get comfortable with these different ions that can form. As I mentioned as well, there can be some trickier ones like silver, cadmium, aluminum. They aren't as predictable, just simply based on their placement on the periodic table, but they can form these ions. What you may also be noticing now is that these metals, right, everything in green, metals like to form cations. So metals predictably form positively charged cations. These transition metals is what we call this group here. They are trickier to know because usually they can form one of two different kinds of ions. So iron, like we talked about, iron 2+ and iron 3+, those are both stable electron configurations of iron. That means that iron can lose 2 electrons or it can lose 3 electrons to be either a 2+ cation or a 3+ cation. It will depend on the environment of the iron to dictate which one it forms. Let's do this practice problem now, and I do want to note that there are a lot more practice problems in the main slide deck, so be sure to check out those as well if you want to see more practice. Let's go through this one now. It's not on the main slide deck. Let's talk about this row here. We want to figure out the element symbol, if it's a neutral, cation, or anion. Here we're given the number of protons and the number of electrons looks to be equal. Actually, before we go into this, I want to review some things that we talked about from part 1 of chapter 2A. Just some quick reminders here. A is the mass number. Z is the atomic number. If the atomic number is not shown explicitly, we can determine the number of protons and the atomic number based on the element symbol. For example, if we were just given the fact that nitrogen has a mass number of 14, well, what about the atomic number then? We can find that. We go to the periodic table, we find nitrogen. It has an atomic number of 7, therefore it has 7 protons. Similarly for phosphorus, let's say we were just given 31p. What does that mean? Well, we don't know the atomic number just looking at this representation of the element. We go to the periodic table though, we see phosphorus, it has an atomic number of 15. Atomic number of 15, all isotopes and all ions of phosphorus will always have 15 protons. Next, if looking at the periodic table gets a little bit confusing to tell what's the mass number versus the atomic number, well, remember that the mass number is going to include the atomic number. It's going to include the atomic number as it's the atomic number is the number of protons. That means that the mass number will always be greater than the atomic number, right? Because the mass number has the neutrons included as well. The only exception here is our unique element of hydrogen. Hydrogen has an atomic number of 1. That means it has 1 proton. Hydrogen has a mass number also of 1. That means there's no room for any neutrons. So that's correct. Hydrogen has no neutrons. I should say this isotope of hydrogen has no neutrons. What's the number of electrons, just to practice? Well, it would have 1 electron for a neutral atom of hydrogen. What about H+, just for practice? That's a cation. That means it lost 1 electron. So this form of hydrogen actually only has 1 proton. no electrons, and no neutrons. Next, for the number of electrons, like we just talked about, for neutral atoms, it will be the same number of protons and the same number of electrons. So number of electrons is equal to the number of protons for a neutral atom. Then, as we just learned for cations have lost one or more electron, so we need to take that into account. They will be positively charged. Anions are negatively charged, meaning they have gained one or more additional electrons compared to the neutral form of the element or of the atom. Let's go ahead and now work on this one. So we saw that 42 protons, 42 electrons, that's got to mean this is a neutral atom, right? It doesn't have any fewer electrons or any more electrons than it does for the protons. How do we figure out what this element is? Well, we go based always on the number of protons, so 42. 42 protons, therefore atomic number 42, so this is MO. This is molybdenum. So for molybdenum, we'll put it right here. Okay, what about this one? We have 35 protons, but we have an extra electron. So this is not going to be a neutral atom. Let's figure out the charge that it'll have. It has 35 protons, 36 electrons. The net charge then is -1 overall. If this has a negative charge and it's gained an additional electron here, we know we have an anion. Which anion do we have then? Well, we always go based on the number of protons, so 35. 35 protons, an atomic number of 35, that means we're working with bromine. What kind of element is bromine then? Well, it's a halogen, right? It's in group 7A, so it's one of the halogens. So our element is bromine, that's the symbol. It has a net charge of -1, so this is how we denote that. Okay, so we got this one, we got this one, now we'll work on the third one. So here we have 2+, that means that this is a cation. We know that right away. How many protons? Well, let's go look for this element symbol here, Be. For Be, that means we're working with beryllium. That means it has an atomic number of 4. Number of protons then has to be 4. If there's an overall net charge of 2+, then how many electrons does this cation have? So 4+ ends up at 2+. That means there's only 2 electrons present, 2 negatively charged electrons, right? Because then we'll have 4+ plus a -2, that's a net 2+. So we can fill in 4 protons, but now this only has 2 electrons. Here is the final answer from what we just did. Now we're on to this topic of finding isoelectronic atoms. Iso is the prefix for equal, so isoelectronic atoms or isoelectronic species, these are atoms that have the same number of electrons. So equal for iso, and then this portion, think electron, same number of electrons. I put another reminder in here where neutral atoms have the same number of protons as they do electrons. However, for cations that are positively charged, they have lost one or more electron. Anions that are negatively charged, they have gained one or more electron. The example that's in the main slide deck is here. If we have neon, we know its atomic number. For a neutral atom of neon, it's going to have the same number of protons as it does electrons, so that's 10 and 10. Now for magnesium, its atomic number is 12, so it has 12 protons, but here we note that it's magnesium 2+, so a cation of magnesium. That means it's lost one or more electrons. For this to end up with a 2+ charge, it means it's lost 2 electrons, leaving this to have the same number of electrons as neon. Neon and this cation of magnesium or magnesium 2+, these are an example of isoelectronic species. You can follow the pattern here as well, including these anions that are also isoelectronic species of neon. In fact, Na+ is an isoelectronic species of O2-. So these are all isoelectronic species of one another, not just to neon. Let's try this practice problem. Write the chemical symbols for 3 different atoms. There's more than just 3, but for 3 different atoms or atomic anions with 36 electrons. So for 36 electrons, for the neutral atom, that means it will also have 36 protons. So let's start there. I just cropped and have one small region of the periodic table. So krypton has an atomic number of 36. It has 36 protons. So krypton is definitely one species that has 36 electrons. Now here we're told to name anions with 36 electrons. We'll also practice with a cation as well. So for anions, we know they have gained 1 or more electrons. So to figure this one out, we can go to the left-hand side of that element, or we can go down here. So we're going to follow the order of the atomic numbers. This is 36. We'll come back to rubidium. Let's stick here with bromine. A neutral atom of bromine has 35 protons and 35 electrons. To make bromine have 36 electrons, we can make that an anion, so we can have it gain 1 electron. When bromine gains 1 electron, it'll have an element symbol of Br minus. So an overall charge now with 36 electrons. So 36 electrons, still with 35 protons, leaves it with an overall -1 charge, and then being an isoelectronic species of krypton. Let's go one further back now. So selenium, with an atomic number of 34, that means it has 34 protons. For a neutral atom of selenium, it'll have 34 electrons. To make this into an anion with 36 electrons, we would have to add 2 electrons, making it overall have 36 electrons. That's going to make selenium have a charge of Se, so that's the element symbol, and then it's going to be overall 2 minus, right? So 36 electrons, but only 34 protons, leaves it with a 2 minus charge. So we've talked about krypton, bromide, and selenide, just to get used to hearing these anions with that IDE ending. We weren't asked about a cation, but let's just talk about this one real quick. For rubidium, it has an atomic number of 37. That means it has 37 protons. For a neutral atom of rubidium, it'll have 37 electrons. Well, it's a metal, so we could make this into a cation, right? So metals like to be cations. They like to form cations. So to form this into a cation to have 36 electrons, we could take away 1 electron. When we take away 1 electron, this does become a cation now with only 36 electrons, but 37 protons. What would the charge then be on rubidium? There's 1 more proton than there are electrons, leaving this just +1 as its charge. So this is another option if we were asked about cations as well. In our question, we just were asked about anions, but I wanted to go through this example as well. That is the end now of Chapter 2A. Hope you're all doing well, and I will talk to you next time.